So I wanted to do a quick video talking about the relationship of the potential energy function to the forces that they're associated with, and then look at these diagrams a little bit to see the information that we can get from that. So in this chapter, we learned another relationship between work and energy, where we're thinking about potential energy instead of kinetic energy. And so we learned that the work done by a force, and it is important that these two are linked, we're talking about the work done by that force, is also equal to the decrease in or minus the change in the potential energy. So those are related. So if we take away the integral form, what this would look like would be a little bit of work, the increment of work dW would be equal to F dotted with ds, and that would be equal to minus du. So all we've done is we've taken away the integral, and so instead of finding the total amount of work or potential energy change, we're just finding the increment of it. Now, if we want to make this simpler, because this involves a dot product, we can think about maybe the force being in the x direction. And so then this can be rewritten as f of x times dx is equal to minus du. And now we get a relationship between the force and the potential energy function, in that the force is related to the derivative of the potential energy function, which is actually really helpful for us. So for instance, let's look at this potential energy function that we work with a lot in this chapter, the potential energy of a spring, just 1/2 kx squared. So think about this expression, and what does it mean with respect to this graph? It means du dx is the slope of a tangent line for this curve. So the force is actually related to the slope, except that it's negative. So for instance, let's think about a point right here, and if I drew a tangent line, du dx would be positive because that has a positive slope. But that actually means that the force of the spring is negative or directed to the left. Likewise, if I find a point right here and find the tangent line, the derivative here is negative, and the force of the spring is to the right because it's positive. And that's exactly what's happening with a spring, is that the force is always trying to take it towards the equilibrium position, which is x equals 0. Notice here, du dx is equal to 0. That's an equilibrium position because that is where the force is 0. That defines what the equilibrium position is. And so this is how we can make something or think about what does this potential energy function tell us about the force, and also what else can we be reading about off of the graph. So the places on the potential energy function where the slope is 0 is actually where the equilibrium positions are. Now, when the equilibrium position is positioned in a way that on one side of, and on both sides of it, the force is always pointing towards it, so that means that in this system, the object is always being pushed towards the equilibrium position. That makes it a stable equilibrium. If you wanted to use sort of math terms, this is where it's concave up is going to be a stable equilibrium. If it looked like the other way, if it was concave down, we would actually find that the forces were always pushing away from that equilibrium position, and that would be an unstable equilibrium. Now, I wanted to just get my eraser here because I want to do a little bit more with this graph. because we want to also talk about energy with respect to this graph. Now, the amount of energy that the system has is always going to be split up between kinetic and potential energy. So we might make a line like this, a horizontal line, because in the end, the vertical axis of this graph does represent energy because it's graphing potential energy, and that's energy. But what if I say this is the total amount of energy that the system has? Well, then that means where the potential energy function intersects the energy, that's going to tell you the bounds of the movement, because it can't go beyond that location. At this location, all the energy, and this one too, all the energy would be potential energy. It would have no kinetic energy, so it's not going to go anywhere. So this vertical distance represents the potential energy of the system. Now, in a case where we're not at the end points, here, this represents the potential energy of the system, and this actually represents the kinetic energy of the system. Of course, that makes sense. We know and have learned that the total amount of energy is equal to the kinetic plus the potential. And so we can actually do a lot with these graphs that we probably didn't realize. We can find information about the force. We can figure out whether there's a position of equilibrium. And then we can also, given a maximum value of energy, we can see how, for instance, as this object moves between these two endpoints, you can see on the graph how the energy is being switched between kinetic and potential. At the endpoints, all the energy is potential energy. At the equilibrium position, because U is 0, that means all the energy right here would be kinetic. Somewhere in between, it's a little bit split in between. Now I wanted to look at just one more graph to talk a little bit about how this energy is split up. And it's a graph that I ended up asking a lot of questions about on the top hat. So it might look pretty familiar to you, and I'm just going to sketch it really quickly here. So this graph, again, it was some potential. I don't know what it's for. Doesn't matter. It looks something like this. Now, in this scenario, the object has two equilibrium positions. In this location, because of the slope of the graph on either side, the force will always be pointing towards that equilibrium position. This is a stable equilibrium, but we already know that, if you remember that I said it would be concave up if it was stable. This location, if we look at, because where the slope is 0 is another equilibrium position, but if I look to the left and the right of that and look at the slopes, I would see that it would indicate that over here the force would be pointing to the right, and over here, because the slope is positive, that means the force is negative because of this relationship. Over here the force would be to the left. So that means actually if I had an object at this location, even if it was displaced ever so slightly, the force that this potential energy function represents would push it away from that place, and it wouldn't get back to that equilibrium. That's why we call it unstable. Now, another thing that I wanted to point out, just thinking about this idea, like how much energy this system might have. Notice here, at this location, the potential energy is actually negative, right? The function goes into the negative, and at first that might be a little bit alarming because, like, oh my goodness, how is that right? But that actually tells us that is possible because remember, with potential energy, we can actually use our, we can say that the U equals 0 is wherever we want. The reason for that is because it only actually matters what the change in potential energy is, and so that's all that we really care about. And so if the fact that the potential energy is 0 somewhere, it just doesn't even really matter. Of course, here is the potential energy, here is positive, and then this would represent the kinetic energy. And so I just wanted to go through that so that we could understand sort of a bunch of different things. There's so much in this last part of the chapter, and sometimes we're rushed, and so I wanted to make the video to go through some of this. And so thinking about how the potential energy function, first of all, to recognize that it's always associated with a particular force, and then we can see the relationship between the graph and the force is given right here, and then how we work with these graphs to sort of interpret this information, and understanding stable and unstable equilibrium, and how the energy can be split up between kinetic and potential. So hopefully that's helpful, and I will see you in class.